Welcome everybody to Network Automation Horizontal Scalability. My name is Wendy Wheeler. Next slide, Cheryl. Next slide. This is the Virtual Network Automation Special Interest Group, the NASIG. Our leaders for this particular SIG sessions are Chris Powers and Wendy Wheeler. Next slide. Our presenter today is Sriram. He's a developer at HP for HPNA. Next slide. Housekeeping. This is a live session and is being recorded so that you can watch it at any time. The recording will be available to all members. We will have a Q&A after this session, so please put your questions in the question pane and we will get those answered for you very quickly after the presentation. Next slide. Little instructions. You will see a webinar control panel. That's where you put your questions in and kind of maneuver in that way. Next slide. And go ahead, Sriram.
Thanks, Wendy. Hi, good morning, guys. So today we are going to talk about the horizontal scalability and the failover. As before, let's define the agenda and then we'll get into do a deep dive into the horizontal scalability. So what's discussed today? So we're going to talk about the HS topologies on NA version 9.11. And the good news is that 9.11 got released yesterday, so you should be able to get hands on the bits and start playing around with that. Then we'll talk about the core status. This is very important because before 9.11, there was no clean way to display the core status in the NA console. So we'll spend some time on the core status. Then we'll get into the failover and failback for the HS topologies. Then we'll try to compare the topologies and see which one fits to your environment, because every environment, every user is different. So you want to see, we'll compare the topologies so that you can figure out what is the best topology that suits your environment. Then we'll do a demo of failover. This could be a little time taking because we are trying to do a real failover demo here. If time permits, we'll definitely do that. And the next one is, obviously, we are going to discuss some best practices, not necessarily the entire feature set, but based on the last session feedback, I'm going to include some of the configuration options also. So a couple of folks were requesting to talk about the configuration also. How do you configure the particular feature? So I'll be trying to address that feedback in this session. Then as usual, our latest documents are available on the website. You should be refreshing your manuals at regular intervals, and you should be going to that website for the latest information. Okay, what's not on agenda? So we're not going to really discuss about the previous versions of NA, and we're not going to talk about the NA multi-master. As many of the folks know, NA multi-master is one more distributed architecture which NA supports. The goal is not to discuss that in this session. And we're not going to get into the database technologies. We'll assume that we have a database, but is the database a particular type of architecture? We are going to get into that part. And the disaster recovery. So NA from 920 supports a feature called disaster recovery that goes very well with HS, but we are not going to talk about the disaster recovery. This is about horizontal scalability and failover. So as usual, we are not going to discuss about the features and enhancements in this session. That would be for a different one. Okay, now let's jump into the HS. As we know, right, HS is a way to scale out NA. So if you want to put multiple boxes for a NA system, HS is one way to go. So NA supports two main topologies in HS. The first one is called core binding. We'll get into that, what it means. And the second one is called distributed round robin. So these are the main two topologies that NA supports for HS. Besides these two, there are three variations of the above two. So we have two main, and there are three variations of those two. We'll discuss all these five topologies in today's session, and then we'll get into the failover. Okay, before getting into that, what are the based on the feedback I got from the last session, what are the configurations we need to do for HS? What are the additional configurations you want to do for HS with 9.11? So you know all the regular changes in the distributed RCX, but one important thing I want to call out is the one which just got highlighted. So this is a new RCX option that we want to include in HS, that is distributed horizontal scalability true. So this is part of the README, and this is a part of the new HS guide also. By the way, the new HS guide is going to be released soon. The patch is out, the README is out with the patch, the guide will be out soon. So this is a must. If you are on a horizontal scalability and you move to 9.11, you should have this option. Besides this option, there are two more options that are mandated with this 9.11 release, and those get into appserver.rcx and siteoptions.rcx. So README has that information how to hide that. Now, jumping into the topology. So I tried to divide the discussion into three parts. What is the topology means, and when you want to use that particular topology, or when you want to go for that particular topology, and how do you achieve that topology. And we'll try to switch between the presentations on the NEA and try to figure out how the configuration is done and some other intricacies. So the first one is the core binding. So what is a core binding? So before 9.11, we supported this topology, and we used to refer this as the topology 1. So when you want to use, so very simple, let me get a point options. Okay. Even before jumping into the core binding, let me explain my setup which I'm going to use today. So I have 3 core box, 3 core horizontal scalability. The reason I use 3 is 3 is a good number to explain all the features. 2 is a very simple one. 4, we don't really require 4 or more because 3 is the optimal one to explain all the features. So I have 3 core box, and that is connected to a database. As many of you are aware, it supports horizontal scalability on Oracle and SQL Server only. So this database could be either a SQL Server or a Oracle. So that's my setup. And while doing the demo, I have a similar setup. I have a 3 core HS, and I'll be doing the demos on the 3 core HS. Now coming back to the core binding. So when you want to go for core binding, so when you have networks that are accessible only to certain cores. For this, in this example, the network 1 is accessible only to core 1, the network 2 is accessible to core 2, and network 3 is accessible to core 3. So there may be scenarios where user environment could be divided like this. For example, they may have certain rules that all the SNMP information should be sent from network 1 if that particular box is in some other network. For example, in this one, let's say where the core 1 is. So when certain parts of the network is accessible only to certain cores, we want to go for this, and we'll discuss about some more pros and cons. And how to do that? To do a core binding topology, the first thing you want to do is you want to create a security partition. So the way you create a security partition is when you're trying to create a partition, it asks you to associate particular devices or the groups. So your entire inventory you are dividing into partitions, and each partition you are assigning it to a particular core. Now, when the tasks run, they check. For every task, there will be a device because it has to run on a particular device. From the device, it checks which partition it belongs to. And after that, it checks which partition that core is associated to. And it runs on that particular core. And I'll give you a small demo to show the configurations. But the important thing is you break into partitions, and based on the partition association to the core, the tasks are run on that particular core. And the configuration changes really. In the distributed.rcx, there is an option called bind task to core. It has to be true. Basically, you are binding tasks to a particular core, and the way you are doing is using security partitions. Now let's switch quickly to the NA console and see what it means. So in this one, again, I have a 3-core box. This is a core 1, this is a core 2, this is a core 3. I have all the 3 NA core consoles open. I'll go to the core 1. Let me see what partitions I have. So I created 3 partitions beforehand. So each partition has around 450 devices. So I have totally around 1500 devices. So the way I did is I equally partitioned. I created 3 partitions, each around 450, and associated the partition to core 1, the first partition, and the second one to core 2 and core 3. Now, when I launch an inventory snapshot, some task and inventory, all the tasks that belongs to devices of partition will run on core 1. All the tasks that belong to partition 2 will run on core 2. Now, switching back to the presentation. Yeah, so just to recap, use partitions, and you associate the partitions to the cores, and all the tasks run on the particular cores. And when you do this, when certain cores can access only certain parts of the network. Now the second one is called distributed round robin. This is referred as a topology 2 in the current documents, the one before 9.11. So here, during the task creation, a core is decided based on the device. So here, let's say I create a new task. Based on the device, I decide which core it has to run. The reason we do is, let's say you have 2 tasks on the same device. I want to make sure that 2 tasks are going to the same core, because we don't want to run multiple tasks on the same core. And if the second task is a duplicate of first one, we want to identify that and eliminate the duplicates. Let me paraphrase this again. So during the task creation, a core ID is decided based on the device the task is supposed to run. And the reason we want to do is, we want to run all the tasks belong to a particular device, let's say X, on the same core. For example, I create a task on device X, and it chooses core 1. And after a couple of moments, I created a new task 2 on the same device X. The new task, I want it to run on the same core 1, because I can decide whether it's a duplicate, and I can make sure that no 2 tasks are running on the device X at the same time. Yeah, that's pretty much the next point we covered. All the associated tasks will run on the same core. Yeah, duplicates are handled. That's what is distributed round robin. And when you want to do that, so it's very clear, right? When the network is, all the cores can access the network. And we'll talk more about that in the failover again. How do you do that? Again, it's simple. Remember the configuration we talked about? We just turn that into false. We turn that into false. Now, going further. Stephanie, could you go ahead and do the polling for question 1 and question 2, please?
Okay, I've launched the first poll, and their answers are still coming in. They're still coming in. Let you know when everyone's voted here. We're almost there. Okay, I'm going to close the poll. Oh, wait, there's a few more coming in. Okay. All right. Now, can you see the answers?
Is it possible that I can take the answers after the session is over?
Yes, absolutely. So.
Thank you. So Stephanie, just to make sure that we did a polling on the question 1, right?
Right, right.
Okay.
So 100% chose configuration management. That doesn't make. And then, can you see the answers there on your screen?
I don't see it, but it doesn't mind. So you already gave me the answer.
Okay.
Perfect. So I'll keep going, and we can do the.
Here, share. There. Now you should be able to see it. How's that?
Oh, perfect. Perfect.
Okay.
Got it.
All right.
Okay.
All right. Second question.
Yeah, please.
Okay. All right. Here's the second question. All right. They're still coming in. Okay. I'm going to close it. And I'm going to share it. Can you see that? Okay, there we go. It's about a 50-50 split. Interesting.
50 split between the 2 and 3 options, is it?
Single core or multi-master?
Okay.
46% for single core and 54% for multi-master. Okay.
Okay.
All right.
Okay. So, perfect. Let's keep going. So now we talked about the primary topologies. Now we'll talk about the variations. What are the variations for these 2 primary topologies? The first one is core binding variation 1. This is referred as the topology 3 before 9.11. So the important thing is it's the same as the core binding topology, but except that 1 or more cores is dedicated for the user interaction and user tasks. So it's very important we understand both. That means if a user wants to do some reporting, he's going to use this core 3 in our case. And if he wants to run some tasks, so you can launch tasks, but those tasks will be run only on core 3. So when you want to do this, obviously, if user is trying to launch some device tasks on core 3, the core 3 should be able to access the network. The task should be able to talk to the network. So that is one important thing to note. And the other way is you don't want to publish all the codes to the regular NA consumers, NA users in your environment, so you'll just publish the core 3. Another thing we need to understand is, let's say for example on core 1, you're running a task on device X, and the user also launches a task on device X, which runs on core 3. So there is a chance that multiple tasks could run on the same device. That's possible. Now, how are you going to do that? It's very simple. You go to the NA admin settings server, and there are 2 options. The first option, you will enable it on any one single core. It will get synced across the cores. And the second option, you want to allow only on the core. In our case, it is core 3. Let's just go ahead and show you that those 2 options. You go to admin settings server, go all the way down. So we are referring to these 2 particular options. The first option you enable, it will just sync across the cores. And second one, you want to do it on the core, which is you are going to reserve only for the users. So that is the core binding variation 1, which is a dedicated core for the user interaction and user tasks. Now the second variation in the core binding, it's basically in this one, it's very similar to the variation 1, except that you can't run tasks on this core 3. It's just only for the user interaction. And how do you do that? Again, it's simple. You go to you just enable this one and just leave it this way. Disable it. And the other settings are same as core binding. And the other important thing, which I didn't mention here, is in these two variations, you don't want to associate any partitions to core 3 in our example, because the core 3 is reserved for user interaction. And I didn't mention that in the slide, but that's very important. Because if you associate any partition to the core 3, then obviously those tasks has to run in core 3. So we are mixing the user interaction and the tasks also. So for the variation 1 and variation 2, we shouldn't associate any partitions to core 3. In our example, it's core 3, or to the core which you are reserving for user interaction. That's very important one. Now, going to the next one. This is the distributed Roundrobin with the ability to reserve a core for a user. And this is a new topology that is with 9.11. So here, it works very similar to distributed Roundrobin, except that we reserve one core for user interaction, or one or more cores. In this example, I'm just showing as one. So again, the same rules apply as distributed Roundrobin. All the cores should be able to access the network. In addition, probably besides reserving this core for user interaction, probably you can do some API integrations to that core also. It depends upon how you want to isolate the system load. And the reason we are supporting this one is this gives a very clean way to isolate the task load from the user load. And I'm sure that certain customer environments require that. So too much system resource usage during the tasks running won't affect the user experience, and vice versa. Let's say, for example, a user is running a major report, and you don't want that to affect the regular task running. So you want to isolate the task load and the user load. And how do you do that? There is a UI option right below the one which you discussed. So reserve this core for user interaction. In a HS system, this is what is going. Just enable that. That reserves that particular core for user interaction in a Roundrobin. And other options in the distributed .R6 are the same as distributed Roundrobin. Okay. We'll get into the next one, which is very interesting. That is our discussion on the core status. Before doing that, Stephanie, could you do the third question poll, please? Stephanie?
Okay, it is launched here. So everyone can go ahead and vote. They're still coming in here. Let's see, let's give everybody a couple more seconds here. Okay. I'm going to go ahead and close it. And I'll share the answers. All right. Can everybody see the answers?
Could you read it for me, please?
Sure. It's actually an even split. 33% for now with NA 9.11, 33% within 6 months, and then 33% with no plans or not using multi-master.
Okay. So I think, yeah. So that's a good question. Yeah. Thanks, Tiffany. Okay. And thank you guys for doing that poll. That's going to help us. Okay. Now let's get into the next one, which is the core status. And why do we need to understand the core status? We have multiple cores. We need to understand what state the core is in, whether is it reserved for a user interaction only, or is the core shut down, or is the core is done because of the hardware failure. So there are many use cases where you want to understand the core status. It's not just for the user visibility and for the NA housekeeping also. If a core is down, obviously I don't want to give that core any tasks. So understanding and having a dynamic core status is very important. And we'll see why it is. So we have an improved core list page. If you go to the admin distributed, there is a page called core list page. Previously, it never used to refresh the true core status. Now it does. And these are the four possible core status. The first one says it's running fully functional. So let me go ahead and show it. So as I told you, this is a 3 core HS. Let's go to the admin and distributor, and this is the core list page we are talking about. This is how it looks like in the new patch, that is 9.11 HS only. Multi-master, this we won't be saying this one. So these core statuses, since we have 33% still on multi-master, so I thought I'll just try to explain the differences also. The true status of the course won't be reflected on the multi-master. This is only the HS feature only. Okay, now we have 3 cores here. I have 301, 302, and 402. These are my core 1, core 2, core 3. And right now they're in a running and fully functional. What does it mean? It means a normal NA running state. These are not reserved for any user interaction. They are not shut down. They're very clean. And they're running. The second one is user interaction only. That means you enable that particular option. The option is, we discussed about that. In a distributed round robin, we enable this option. This is the score for user interaction. If we enable these two, that is the core binding options, the status won't change. That is due to some technical limitations. But when we do this one, the new option which we introduced, the status is truly reflected there. Okay, now coming back to the core list page. So we have 3 cores which are running in running state. Let's continue. So we have 2 more core down states. The third one is called stop, which is a normal shutdown. Let me do that so that we'll know, we can talk about that. So I have a core, this is a core 1. So just to make it interesting, I'll just shut down core 2. Core 2, let me log into my core 2. These are Windows boxes, and I'm running an Oracle database for this demo. So I'll go ahead and do a NA stop on core 2. So what I'm doing is I'm trying to demo the normal shutdown. So that means it's a user-initiated shutdown. What does that mean? Suppose you did a true control stop, or you are trying to install a patch, or you want to do a regular maintenance. So instead of pulling the plug to the system, you did a proper shutdown of the system. Then that is considered as a normal shutdown. Normally, we shut down the true control services. Now, this is the one. So let's go back to the NA. So I'm on core 1, and core 2 is down. Let's just confirm it. I'm trying to refresh the NA console. It should time out. It's trying to connect, it timed out. So core 2 is really down. Let's see what my core list page says that. So yeah, now it shows a true state of that core, which is stopped, normal shutdown. So this is going to help the users, okay, for some reason if the one core is gone down, and it's going to help the NA system also. Now let's say if I start a new task, an inventory snapshot, none of the new tasks will be assigned to the core 2 because the core 2 is shut down. And the other important thing is the core 1 and core 3, they won't even try to communicate core 2 because they know that core 2 is down. So that is, we just talked about the status where you did a normal shutdown. Now the next one is the abnormal shutdown. This is very interesting. This means you didn't do the, user didn't do the true control stuff. This is due to the hardware failure or network failure, or the core is not able to connect to the database, or some other hard failures. So when I do the failure demo, I'll demonstrate this state. because it will be redundant if I do it now and then I have to again do it for the failover. So just to save some time, I'll demo this during the failover discussion. So to just summarize this, we have 4 states and 3 are very important. The first one is the running, so it shows that it's running and everything is good. The next 2 are core down states, which is nothing but core stopped, and we differentiate between a normal shutdown and a abnormal shutdown. That's about the core status. And initially I was not sure that whether I want to get into this core status. This is getting in little into internals, but there was a feedback in the last session. They wanted to know a little into the working of the feature, so I added this one. So let's very quickly go through what it means. So when any core starts, so when you do a true control start, it just updates the database with running state. So we know which state the core is in. When you do a stop, core stop, that is a proper true control stop, it updates saying that it's a normal shutdown. So we'll know the states. It's very simple. And besides these 2 steps, with 911, we have something called core heartbeat. That means each core periodically updates the database with the running status and timestamp. And the default interval is 1 minute. And that's the optimal one. But for any reason you want to increase or decrease, you can always do that referring to the new HS guide. But I sincerely recommend 1 minute because that seems to be the optimal one. This is a very lightweight heartbeat. So every core, it updates the database saying that I'm alive at this time, and it keeps doing that every minute. So what happens? So in this case, right, core 2 did a normal shutdown. So that means it went through this step. It went to the database and said normal shutdown. But I'm seeing this page on the core 1. How does core 1 came to know that core 2 is down? So for that, you need to understand the next one. So every core checks the other core status periodically. So in this case, what happened is core 1 and core 3 were checking the core 2 status. And core 2 is down in this case, but if it was up, it would be checking core 1 and core 2. So every core will check the other core status. So in this particular case, my core 1 figured out that the core 2 went down, and it updated its information saying that it's down, and that's why we are able to see it on the console of core 1. So it's very simple. 4 important things we want to know. When a core starts, it goes to the database and says, I'm running. When a core stops, it says, I'm shut down, normally shut down. And the way we figure out abnormally shut down is based on the next 2 steps. Like each core has a heartbeat, and each core checks the other core status. So, and I want to underline this particular statement, which is the last one. So what it says is, okay, now for example, core 1 and core 2, in this case it's a normal shutdown. Let's say core 1 and core 3, they didn't see any core 2 update for, let's say, 10 minutes. That means they conclude that core 2 is down, and it's not normally shut down, it's abnormally shut down. Because, right, it's still showing as running, but it's not updating its timestamp. So it will decide as an abnormal shutdown. So for the other cores to figure out that core 2 is abnormally shut down, it takes at least 10 minutes. It's not instantaneous. We don't want to do it instantaneous because it may generate a lot of false positives. So we'll wait. The core 1 and core 3 will keep watching core 2. They know within a couple of minutes, they'll know, okay, core 2 is down. But they want to wait and see if core 2 doesn't come up in 10 minutes, and they decide that it's abnormally down. And we already covered the next point, which is basically based on the core status, we decide whether you want to assign the task or whether you want to talk to the core or not. That is about the core status. Now what I'll do is, Wendy, do we have any questions? So it's a good time to talk about topologies.
No, we do not have any questions at this time.
Okay, perfect. So let's continue on the failover and the failback. Okay, even before getting into the failover, I think let's define what is a failover and failback in the context of NA. And this is general definition also. So failover. Failover means when a particular core is down, or whether it's normally down or abnormally down, the other core should be able to pick up its work. In our case, its work is tasks, is a work envelope. So basically, let's say in our example, core 2 went down. We did a normal shutdown, but it didn't. It had some tasks assigned to that, but it didn't come up after a long time. For whatever maybe the reason, it was regular maintenance, or we are refreshing the hardware. So there could be some tasks associated to the core 2. We want to take over the core 1 and core 3 wants to take over that and continue. So this happens automatically. Failover is an automatic one. Okay, what is the implications on the HS system? The throughput of the HS system could go down because we lost one core, but the functionality is not affected. Previously, if the 3 cores are running, let's say the group task was taking 5 hours to complete. With 1 core down, obviously it can't complete in 5 hours because we lost 1 core. So it may take 7 hours to complete. So the throughput of the system will be down, but the functionality is not affected. That's one of the goals of the failover. So failback, it's straightforward. You restore the core to the state before the failure happened. So that means once it's a failback, you start assigning new tasks, make the core as a part of your RMI communication, everything. So the two concepts, failover and failback, and we'll discuss how these work with the topologist. Okay, even before getting into the topologist, what event triggers the failover? There are two things as we talked about. So we don't want to trigger failover when everything is running and good, right? Obviously, everything is fair, fine. So we want to trigger failover when the core is down. The core could be down because of two conditions. One is the abnormal shutdown, one is the normal shutdown. So let's talk about abnormal shutdown first. That's more interesting. So when our core 1 and core 3 in our scenario decide that core 2 is abnormally shut down, they will trigger the failure immediately. But you remember, it takes for core 1 and core 3 10 minutes to figure out the core 2 is down. But you can configure it, by the way. Default is 10 minutes. You can make it 5 minutes or a couple of minutes. So immediately as a core 1 and core 3 figure out that core 2 is abnormally shut down, they'll trigger the failover. And it takes 10 minutes for core 1 and core 2 to figure out that the core 2 is abnormally shut down. And when you come to the normal shutdown, failure is triggered after 30 minutes. We don't want to trigger, we don't want to do an aggressive failover during the normal shutdown. The reason could be, I'll take an example of patch install. You want to install a patch. So you did an NA stop, you went for coffee, you came back and you started installing the patch. So it may take a couple of minutes. By default, it's 30 minutes. We'll wait and see. The core 1 and core 3 will wait and see if the core 2 is down for more than 30 minutes. After 30 minutes, they will initiate the failover. If you want to override, you can do that. Again, that information will be in the new HS guide. Okay, so we just talked about what events trigger the failover. Now we'll get into the details. What failover actions happen with the core binding and what actions with the distributed round robin, because we have only two main topologies. So failover. So again, in this example, what I'll do is, again, I'll take core 2 as the one that's either normally shut down or abnormally shut down. So I just made it a little red there. So remember, the task execution in the core binding is bounded to the security partitions. So the first step in a, let's say core 2 went down, and we have partition 2 associated with the core 2, and core 2 went down either normally or abnormally, and we are triggering the failover. The first thing we need to do is we need to move the security partition to either core 3 or core 1, and you can specify that in options. In the R6 option, you can specify what is the backup core for the core 2. But you remember, let's say you did a core 2 backup is core 3. That means core 3 should be able to access network 2 also. But your network is such a way that a core 3 contact to core 2 or core 1 contact to core 2, sorry, network 2, then obviously failure is not possible on your network. So failover is there, but it depends upon your environment whether you can do a failover in Roundrobin, sorry, in a core binding topology. Now, what are the actions when we trigger, when we move the tasks? Let's say core 2 has some running, some pending, some waiting, some requested tasks. First running. All the running will be moved to failed for the down core. We don't want to move a running task to a different core. First thing is that would be very complex, and other thing is we don't know which state the task was in when the failover got triggered. So we'll just mark it as a failed, and you can do the search. If you remember the session 1, you can do a search based on failure type for these tasks that got failed while doing the failover. And the pending would be moved to a pending to the new core, and the waiting would be moved to the pending, because we don't want to move the waiting to waiting because of the life cycle we talked about that. So we move to pending. From pending, it will move to the waiting to the new core, and it will continue to run. Requested would be moved as requested to the new core. So important thing is all the task load on core 2 is moved to the core 3. Core 1 didn't get anything. So the core 3 got everything from core 2 because we moved the security partition from core 2 to core 3. Because we can't divide the partition and give half of the partition to core 1, after the partition to core 3. That is not possible automatically. But if a user wants to do that, they can do that. So first thing we did is, to recap, we moved the partition, then we moved the tasks. Failback. There is no automatic failback because let's say core 3 got the partition 2 because of the failover. We don't know where the partition 2 came from. So user has to explicitly reassign the partition to partition 2 to core 2 once the core 2 is back and up. So it's a manual failback, an automatic failover for core binding. Let's see how this looks with the Roundrobin. With the Roundrobin, you move the tasks from the down core to other running cores. In this case, it would be core 1 and core 3, because all the 3 cores are accessible to the network, and we don't have the partition limitation here. So let's say core 2 was running 100 tasks, either in running, pending, waiting. So each core will divide those two. Like core 1 will get 50, core 3 will get 50. So they divide the load. And what would be the task states? So they'll move running to fail. Again, we don't want to move the running task to other cores. And pending to pending, waiting to pending, requested to requested. It's the same as the previous one. Failback. So we have an automatic failback for the Roundrobin also. What happens is, if the down core, the 2 is up, and then it will become a part of the whole topology, and all the new tasks, they will be getting associated to all the 3 cores. But the tasks that already got moved away from core 2, just because the core 2 is up, we are not going to reassign them. All the new tasks will start getting assigned to core 2 also. That's the difference we want to make it. So that's about the failure actions with the distributed Roundrobin. Now, right, we talked about core binding and the distributed Roundrobin, but which one I want to go? How do I compare these two topologies? So this slide is about comparing the topologies. So the first one is, we already talked about, we want to go for core binding when the certain parts of network is accessible to certain cores only. And when we have all the devices accessible to all cores, we want to do the distributed Roundrobin. And next point is very important. The ability of splitting the load among cores purely depends on the user ability to create partitions. If the partitions are unequal, in general, that would be the most of the times the load on the cores is different. Whereas in distributed Roundrobin, the load split is almost even. So it will almost equally distributed. When I say almost, let's say I have 1,500 devices in my system. It won't be 450, 450, 450 or something like that, or 500, 500, 500 like that. It would be around 460 in one, 470, 510, something like that. It's almost equal. The next one is, the next difference is the failover time. During the failover in the core binding, we just saw that all the load from the core 2 moved to core 3. Whereas in distributed round robin, it is distributed among the running cores, which is 1 and 3. And the other difference with the core binding is failback is manual, whereas failback is automatic with distributed round robin for all the newly created tasks. So that is the comparison between round robin and core binding. And based on the questions, probably we can elaborate more on this one. Before getting into the new events, let me talk about the events, then Stephanie can do a next poll. Okay, new events. So with 9.11, there are 3 new events that will be showing up in the events. So the first one is whenever there is an abnormal shutdown. That means in our case, core 1 and core 3, core 1 or core 3 figured out the core 2 is down. And they started doing the failover, and they create a new event saying that core 2 is abnormally shut down. And whenever a core is just normally shut down, I think this was one of the high ones many people were requesting, it will do a normal shutdown of the core event. Okay, when you do a true control stop, it will go to the database and say, I'm shutting it down, and it launches an event saying that I'm normally shut down. And the next one is, you remember, the failover of the normal shutdown is not triggered immediately. It will trigger after some amount, and default that is 30 minutes. The next one is, there was a normal shutdown, and there was a failover on the normal shutdown. Then we have the next event called processed normal shutdown of the core. That means the failover of the normal shutdown happened because it didn't come up after 30 minutes. And these events are searchable. Again, our regular reporting search for events, we can do the search for this. Okay, now it's time for the next poll question on the last one. Stephanie, could you please go ahead with the last polling question for the day?
Okay, I've launched it, and everyone can go ahead and vote. Let's see. Okay, they're starting to come in. Let's see, they're still coming in. Give it a few more seconds here. All right, I'm going to close it. And I will share it here. Would you like me to read the answers to you, Saram?
Yeah, please.
Okay, so 17% chose core binding. Each NA core can access only some devices. 8% chose core binding with 1 or more satellites. 58% chose distributed round robin. Each NA core can access all devices. And 17% chose distributed round robin with 1 or more satellites.
Awesome. Thanks, folks. Now it's time for a quick demo of failover. Or I can take a couple of questions. Wendy, do you have any questions?
We do not have any.
Oh, that's interesting. I did expect a lot of questions in today's session. Okay, so folks, that's nice that I'm either making a lot of sense or I'm not making any sense. Okay, so what I did is I started the core 2 as we were doing the polling, and now it's back and running fully. So let's check whether you're able to access the console. Okay. Okay. So let me log into all the 3 cores. So now we are going to do a quick failover demo and just see how these things are happening. So we have 3 cores. This is a core 1, this is a core 2, and this is a core 3. So all the 3 cores are running. That's what we can see. What I'll do is I'll go ahead on core 1, and my inventory is around 1,400 devices.
Actually, Sriram, can I interrupt?
Yeah, please.
Can I interrupt for a second? We do have some questions. My screen was not updating properly. Can we quickly go through the questions?
Yeah,
all right.
Wait. How about this? Sorry to interrupt. Actually, what happens is when I do a failover, for 5 minutes we have to wait because the failover will get triggered. So I will take the questions during the time.
Perfect. Thank you.
Thank you. So guys, as I was saying to Wendy, let's go ahead and do the start the failover, and we are going to do an abnormal shutdown. That means some hardware fail happened on the particular core and the core is not accessible. So as we remember, right, by default it will take 10 minutes for the failover to trigger because we want to avoid the false positives. For the demo, what I did is instead of waiting for the 10 minutes, I did an override in the RCX option, which I'll show it to you guys. So if I go to that and I see my distributed my adjustable options, I did an override. That says abnormal shutdown grace time. I made an override of 300 seconds, which is 5 minutes. So during that 5 minutes, we'll take a couple of questions. Okay, now without wasting time, I'll go ahead and click the, I'm going to do a snapshot task on my 1,400 devices, and my entire inventory in this small NA setup. So I started that. So right now, if you go back to the slide set, so let's pick up one example. Okay, this is what we're going to do. So I'm in a round robin. Let's pick the round robin one. Yeah. So my network is core 1, core 2 and core 3, and they're connected to a database here. And I'm in a distributed round robin. Since I started 1,400 snapshot tasks, so they're getting distributed almost evenly to all the 3 cores. Let's see how they show up in our new task load page, which we talked about in the last session. So I go to the core 3, I go to the admin page, and I say task load. So if you see the task load, right, my max concurrent task is 30 on each device, on each core. So it's running to its full max 30. That's the reason the message says that running task matches the maximum, so we are good. And there are around 429 which are waiting. And if you see my core 1 and core 2, remember I'm on core 3. So there it says running tasks are 30, perfect. These systems are running to the full extent. And the tasks waiting are 433 and 433. You see there's a small change between the distribution. It's 429, it's 433. That's the reason I said almost equal distribution. Now, what I do is I'm going to do a hard shutdown on core 2. And since I can't give a demo of shutting down the physical system, what I do is I choose a VM so that I can show you. So this is my virtual center, and this is my core 1, this is my core 2, and this is my core 3. Sorry, there are a lot of other boxes also. Let's say I choose my core 2. So I'm doing a hard power off. So I'm going ahead and doing a hard power off. You're going to shut down your operating system. I did. So it is triggering. So virtual machine is stopping. I just want to wait till it's completed. Okay. It's completed. So I did a hard shutdown on core 2. Let's just confirm from the core 2 console also. I shouldn't be able to access. So it is trying to reach, and I'm sure it's going to time out. So I'll just check my remote desktop of the core 2 also. Even that is gone blank. So the core is really gone down abnormally. Now, on this one, right, so I keep refreshing the task load page. What you observe here is, and you remember, we did a shutdown around 10:55 my time. So what we do observe is, now for the next few minutes, the tasks that are moving from waiting will happen on core 3 and core 1. It shouldn't happen on core 2 because the core 2 is gone down. So let's keep refreshing. See, the core 1 and core 3, it decreased, whereas core 2 is still 382 because there is no code that is running. So let's keep refreshing. See, all the other tasks, waiting tasks are getting reduced on core 1 and core 3, but not on core 2. Okay, it remains at 382. Now what happens is around 11 a.m. my time, because the shutdown happened at 10:55, the failover will get triggered and these tasks will be moved to the other cores and they will complete the execution. Okay, now again, since let's see what does our core list says. They're still saying it's fully functional because they're waiting for that 5 minutes window, because I changed from 10 minutes to 5 minutes, before declaring core 2 is down. So we'll wait for 5 minutes, and Wendy, over to you for the questions.